Hello. I'd like to welcome our participants from around the world. I see we have people here from Japan, Kenya, the United States, and even Scotland. So good morning, good afternoon, and good evening to you all. My name is David Righetzi. I'm from Oxford Intelligence, and I'll be your host for today's events. And behind the scenes, we have Terry Watts from IBX, who is our webinar guru, ensuring that everything is going as smoothly as possible, which he assures me it will. And behind us, we have our sponsors for the event, which is Scottish Development International. Now, we're here for an hour-long discussion and debate on subsea sensors, where we'll cover a number of areas, though with a particular focus on data. How to collect data, how to present it in ways that are not overwhelming given the amount of data that we're collecting, and then how that data can be used to make good decisions. The presentations will provide examples of new geographies, new markets where sensors find themselves, whether that be in construction in the Middle East, environmental monitoring in the Arctic, or in a constantly moving position anywhere over the seven seas.
For now, I'd like to give the floor to Richard Nielsen from the University of Aberdeen, who will provide an overview on some of the issues that the industry is facing.
I'm taking you through some ideas today and challenges in terms of subsea sensing. So let's just have a quick look at the outline to the talk. I'll give some introduction, some ideas of subsea challenges, some ideas on subsea sensors and data requirements, some more detail on underwater sensor networks, and then also some comments on deriving information needed for decision making from the kind of data we get from sensors. And then we'll draw some conclusions. Current challenges in terms of the North Sea particularly are things like small and remote fields, harsh environments and deep water. And these bring various problems. Partly the need to minimize infrastructure cost, the possibility of not being able to have local manned structures because they may not be economically viable, but we still need good quality processed information to make decisions. We've got long and deep tiebacks, maybe up to 170 kilometers west of Shetland. We need control and communications over these long distances. We've got flow assurance problems where we may need sensors at many places, and we've got a need for environmental monitoring. The way forward for this are probably in terms of sensor systems. We need high quality data from sensor systems. We need operational flows, pressures, temperatures, and so on. We also need data on the condition of the infrastructure, but also we need environmental monitoring. And we then need to communicate this data, and wireless sensor nodes and networks are possible solutions for these. Cost-effective, low power consumption, but they also need to be secure, reconfigurable, and we need physically robust systems for underwater environment. So in terms of wireless communications, the advantages of these as well, we have communication possible of asset integrity data. We can also link up with EUV communications, where there may be a limited communication range for the EUV. Brilliant, very good use of wireless communications for backup channels for communication, retrofit for existing equipment, and removal of fiber or copper communications. In terms of underwater sensor networks, we have the possibility of looking at multi-point measurement for flow assurance, distributed leakage measurement, and environmental and reservoir monitoring. Reservoir monitoring at the moment is taken by wired systems, and there's systems in Norway at the moment with several hundred sensors wired over about 1.8 kilometers. Very difficult to install, expensive to install. So some advantages of underwater sensor networks and wired and wireless systems. Wired, very simple power supply. We've got shielded cabling, we've got high data rates. But the disadvantage is very much that we have single point connection failure. One wire goes down, we may lose the whole system. We've got high installation and maintenance costs. Wireless, we've got low installation costs. We can drop it in the water or easily place it. We've got no deep water wire connector problems. We can have automatic rerouting if we have a connection failure. And we've got the possibility of mobility, moving things around or retrofitting to existing plant. The disadvantage is very much in terms of acoustic and electromagnetic interference, reduced data rates, particularly in EM, and limited power, the fact we can't transmit necessarily over long distances or at high powers. Looking at this in terms of power requirements, routing of networks is very important. This slide shows a network of wireless nodes. So each point is a wireless node, And the lines show the routing which would happen in a normal routing protocol. The right-hand graph then shows us that same network, but using a very efficient routing protocol, which minimizes energy usage, and we can say about 70% of usage. As you can see, there's much fewer nodes used, broadcasting over longer ranges, but the net effect on the system is lower consumption, longer lifetime. And to be useful, we need to derive useful information from the data. We need to be able to report this information to allow decision making, and then we need a quick decision to be made. And there are various solutions for this. One is data mining. There are companies like Sibula and BlueFlow who do this type of thing. There's also things like data text reporting, where we can use data, and natural language generation allows us to generate reports. And ARIA at the moment are using this in the Gulf of Mexico on some of the sites there. And then there's possibility of automated decision-making, rule-based, Bayesian reasoning, fuzzy logic in networks, where we can actually speed up decision-making locally without human intervention. So decision-making, some of the ways we might get around this, some of the problems actually associated with these are in terms of data mining. We need to have known events against which we can match data trends. So we can look at data trends, but we need to know what these actually mean in terms of events in the past. We also have, in terms of automated reporting and decision-making, employee and public perception, trust in the system, whether it's seen as being safe, choice of the decision-making system of the ones I mentioned, and also whether the knowledge base we've used for decision-making, is it complete, are there any conditions missing? Having said that, we trust automated decision-making systems like ABS, braking systems, autopilots in flight and so on. So these things can be got around. So just to conclude, subsea sensor systems and communications can assist in meeting challenges by providing high-quality process data and providing high-quality and flexible communications through wireless networks. But there are still areas that need to be addressed. We still need to extract the useful information. We need to be able to report this and provide quick decision-making. So just thank you for listening, and we'll take some questions later on.
I'd like to thank Richard for setting the scene for our discussion, and now I'd like to continue on to a series of presentations on new technologies being used in various settings. For me, the most interesting aspect of these presentations is how sensors are being brought into new environments. And with that thought in mind, I'd like to invite our first speaker in this series, Blair Cunningham from Coda Octopus, to speak. Blair is here to talk about the visualization of data from the seabed. Rather than bombarding an operator with multiple images, Coda Octopus has been working on taking sensor data in different dimensions and combining them into a single feed that allows operators to make decisions more easily.
Well, thank you very much. My name's Blair Cunningham, and I'd like to thank you all for attending this webinar. I'm President of Technology for Coda Octopus, and Coda Octopus is actually part of a larger group of companies. So we're actually multinational. We're headquartered in the US. We have two engineering businesses, Salt Lake City in Utah, and also in the UK, in Portland. I'll be talking about the marine products division of the company, and then we're situated in Lakeland in Florida, Edinburgh in the UK, Bergen, Norway, and latterly in Perth, Australia. Echoscope is a world-unique real-time 3D sonar. So a real-time 3D sonar, if we compare that to other technology, on the top right, you'll see an image of a 3D multibeam. So this is typically a sensor you would either move along the sea floor, and what you'll see is it will gradually build up a three-dimensional image, but we end up with the black marks, which are shadows. We can't see physically past objects. A 2D imaging device is maybe more akin to, like the baby sonograms that you would get. So you can see a 2D representation of an image on the seabed, but we've got no depth perception. We lose that additional three-dimensional capacity. And then the main window is what we're looking at for the Echoscope. And that image that you're looking at there was rendered probably in the time it took the boat to sail past this underwater structure. And we see this incredibly high-resolution real-time image with no post-processing or editing in real time. So the operator can make decisions about what they see in real time, and we can obviously use that for other application points as well. do you need sonar? So I think the biggest problem for most people is when you look at visibility in the water. So what the Echoscope can do is still provide a clear representation of the seafloor or moving objects in the water column, regardless of the turbidity or the resolution of the clarity of the water. So the image on the right is showing a typical ROV camera that we can see, and the image on the left is then what the Echoscope is seeing at that same time. And this allows me to then carry out tasks or construction work in real time. The Echoscope is unique, however, in that we can actually do two things at the one time. So we can either use the system as a camera. So the image on the left is allowing us to see what's typically a large concrete block, in this case used for building breakwaters, but it could easily be a section of a pipeline, it could be a second ROV in the water column, but we get to see that object moving in real time. If you imagine a construction environment, if I'm a crane operator and need to move that object around, I really need a high refresh update such that I can understand the cause and effect of the motion that I'm doing. The image on the right, again, is a similar one where we do 3D complex mapping. The way the Echoscope works is, because it's a volumetric sonar, it images typically 50 degrees by 50 degrees field of view, so much like a camera. But we can then use all of the data that is returned, all the XYZ points that we returned, and we can produce a noise-free image, which is of very high resolution, but automatically we can filter out any of the incoherent data. And the one thing for people that have used underwater sonar or cameras underwater, be it fish, be it sediment in the water, there's always noise and artifacts that appear in the water column which could normally have to be edited out of the scene. To give you some of the benefits of the system, so as we stated, you can use it in zero visibility condition. We can see moving assets, and we can also build up maps of moving assets. So if I give you one really good example is, if I wanted to image a pipeline and I wanted to look for perhaps a leak in that pipeline, we would use perhaps Echoscope in camera mode in real time, and we'd be able to clearly see the leak coming from the pipe. But perhaps one of the byproducts is that once I've gone along maybe the 10 kilometers of pipeline, I wanted to produce a map of the data. Now, typically, you would have to use two different sensors for that. With the Echoscope, however, we can just visualize the data in camera mode, but I'm actually building the map in real time behind the scenes. So we've got lots of really nice applications and multiple things we can do with the system in real time. Some of the applications we're actively involved in are, in port construction and the oil field and renewables, but we're involved in a number of research programs, oil detection, gas leak detection, port security. So this gives you just a little flavor of some of the active work that we're currently doing at the moment. Oil and gas, the pressure is really coming on to complete tasks on time, people to spend less money, and then how do they, what's the cause and effect? You don't want to go out and do a survey, then go away and analyze how you're going to complete the task with no visualization, and then go and do a survey to work out what you have perhaps done wrong. So this gives you the capability that allows you to see exactly what you're doing in real time. So in essence, One Per Business is all about how do we shrink the process that was typically done off, as I described there, survey, process the data, do some planning, execute, and then do another survey, process the data, and review. We can actually do all of this in the same time. So we've got a kind of very, very good system to be able to do that. What we can do also is to bring models into the place. So now the operator not only can see with the sonar data, but we can place models such that they can say, this is where I need perhaps a mattress to be placed upon the seabed, and in real time we can color the data relative to the position of that mattress. So it becomes almost like a computer-guided system, but with very high graphic content to the operator so they understand what they're doing. Typically, the people that are doing these construction tasks, of course, are not surveyors. Just to focus lastly on then one key program that we recently done in the Middle East. They needed to place pipeline sleepers on the seabed. And the problem with the line pipeline sleepers, again, is the visibility problem, but the use of divers. So they had to use divers quite extensively to place these on the seabed. What we did, though, was to come up with a new program such that they could use the echoscope in conjunction with some positioning, subsea positioning. And this time they would be able to exactly see where they were placing the sleepers upon the seabed. So if we look at the objects here, and we can have a look at this model we're seeing, they're not only able to witness the sleeper placed on the seabed in real time, but they can build a pre and post map as they're going along, such that when they come to the end of the survey, they're able to then produce complete survey results. And the productivity gain they were actually able to achieve in this particular case was over 3,000%. They went from laying 12 sleepers per day all the way up to 76 sleepers per day. Anyway, that was all I wanted to show you today. I hope you find this information useful, and thank you very much for your time.
Thank you for that, Blair. Next, I'd like to introduce Tracy Schmield. For me, the most interesting aspect that I've taken out of my sneak peek of her presentation is how sensors are being brought into new environments and how the line between data collected subsea and above ground can blur. With that thought in mind, I'd like to ask Tracy to present on the work she's doing on environmental monitoring, taking sensors into extreme environments such as the Arctic.
Hello, I'm Dr. Tracy Schmield, and I'm based at the Scottish Marine Institute in Oban. I'm the Managing Director of SAMS Research Services Limited, which is a service company that's attached to a research laboratory based in Scotland. We work all over the world. The red dot in this slide shows you where we're based, and the yellow dots show the work that we've worked all over the world internationally with different companies. One of the areas that we work in, and it's our key area, is mining and looking at waste management services. And we are actually the leading people on deep sea mine tailings placement. And this is placing waste into the deep ocean where there's no room on land to be able to store the waste. And through that, we've managed to understand what's happening in the ocean and look at sensors or possible sensors that may help this. So what's important looking at sensors? Well, we need to do environmental impact assessments and operational monitoring. And really, nowadays, we have a lot of technology, and we want to look at environmental monitoring and technology to see how technology can help us be able to see if things are changing very quickly, but also to help save money in the monitoring. So what needs to be done? What technology is available? And can technology be used for real-time monitoring? And can real-time monitoring lower risks? At SAMS, Scottish Association for Marine Science, and SRSL, we use a lot of robotic platforms for marine research, underwater and airborne. So underwater, we look at autonomous underwater vehicles. We look at remotely operated vehicles, ocean gliders for looking at ocean variables. We look at wave gliders. And also airborne, we look at remotely piloted aircraft. And at the moment, what we're looking at is to tie airborne and underwater measurements together so we have a whole picture of the system. Just to give you a bit more information, looking at the autonomous vehicle and some of the sensors we've put on it. Obviously, they're standard. They're equipped with GPS, so you know where they are. They talk to satellites. They have Wi-Fi. And they also have what's a CTD. Now, CTD is a conductive temperature depth monitor that looks at all the different, looks at the temperature and it looks at the conductivity of the ocean, which can tell us a lot of information. It has an ADCP, which looks again at currents and it looks at other parameters in the ocean. And we can also put other sensors on there. It's got a large payload, and this is one of the exciting areas at the moment, is developing new sensors. For instance, maybe looking at heavy metals in the water. Moving from under the ocean to airborne, we have remotely piloted aircraft. Now, these remotely piloted aircraft are small, obviously autonomous aircraft that we put sensors on. At the moment, we're looking at high-resolution cameras. And these high-resolution cameras can look at a lot of detail on the land surface. It's also used for looking at harmful algal blooms in the ocean, looking at chlorophyll, and we're hoping it will look at jellyfish blooms as well. At the moment, the slide you can see here was one that we used to look at litter around the very remote areas of Scotland. So one of the areas, as well as using instrumentation that goes off on its own to make the measurements, is to use a term we use as smart buoys. Now, this is a moored array of instruments that can be put at any place on the ocean, and it stays there. It doesn't move about, but you can put different instruments at different depths in the water, and you can get real-time information sent back. For instance, we can put turbidity sensors, oxygen sensors, temperature, look at acoustic Doppler current meters, ADCPs, and again, it's novel sensors we're looking at now to be able to look at different industries for monitoring. So for instance, for mining, we're very keen to work and develop a heavy metal sensor that can tell when the concentrations of metals are increasing in the water column. One of the sensors that we actually produce and sell at the moment is a sea ice mass balance array, and this is actually an instrument that measures the thickness of sea ice and also the movement of sea ice, and we sell these all over the world to research institutes, to government agencies, to people who need to understand how ice in the Arctic and the Antarctic is behaving, how thick it is it moving, where is it going to move to. And this is really important for installations such as oil rigs, for any industrial application, and obviously for transport lanes in the sea. So I'd like to thank you. That was a very quick summary of what SRSL do in the sensor range, and we're very keen to work with people to develop new sensors. So thank you very much.
Thanks, Tracy. And now our next presentation is going to be from Sveinung Botnan of the Christian Michelin Research Institute. He's here to show us sensors in a completely different light. In the last two presentations, we saw sensors being used in a relatively static context. In this next presentation, however, we see sensors on the move in a sustainable context with a speed determined largely by the wind. With that, I pass on the floor to Sveinung.
Hello, my name is Sveinung Botnan. I work as Technology Director at Christian Michelin Research Institute, CMR for short, in Bergen, Norway. Christian Michelin Research is a non-for-profit research institute with about 170 employees. We are mainly owned by the University of Bergen. In this short presentation, I'm going to tell you about a product developed at CMR, the CMR Sailboy. The Sailboy, in short term, is a remotely operated small sailboat that carries instrumentation. There is no combustion engine. The vessel uses wind to move from one point to the other. Further, the vessel contains two batteries, one for operating the sail and one for instrument power and communication. Some key elements to the Sailboy. The Sailboy can carry 10 kilos of instrumentation with a maximum volume of 60 cubic decimeters, which is the same as 60 liters. The batteries have capacity to last for up to 3 months operation without any recharging. The Sailboy uses satellite communication, and the client can view the position and give new commands through a web interface. Average speed while at sea has proven to be between 1 to 2 knots, depending on wind and current. Why is there a need for such a vessel then? In short, the vessel can replace far more costly and manpower-intensive operations than for manned ships. It can carry any kind of instrumentation that meets the following requirements. The power consumption meets the requirements, which is low power or only powered when needed. The size and weight fits the already mentioned specifications, and the instrument works on a platform in motion. Typical measurements are oxygen, salinity, temperature and pressure, heave, or in other words, wave height, crude oil on surface, oil and gas leaks through downward pointing sonars, wind and current. Now I'm going to tell you about some projects the Sailboy has done in the past years. In 2013, the Sailboy was put to use in the Gulf of Mexico. Please see the map for the route. The project lasted from the 15th of March to the 15th of June and was a success. The Sailboy reported quality measurements of temperature, oxygen, and conductivity, where conductivity and temperature were used to calculate salinity. The longest journey in one direction the Sailboy has made was in 2011 and was from Bergen in Norway to Scotland. This project gave us useful proof about the Sailboy's abilities. First, the Sailboy can survive severe weather conditions, including storm and big waves, without assistance, and be able to operate in winds up to 20 meters per second. Second, the the sailboy sailed about 75% of the time against wind, current, and waves. And third, when facing little wind and current in the wrong direction, the sailboy drifted away from the target. However, it stayed in the predefined corridor and was back on track as soon as the wind was sufficient again, which is more than approximately 2 meters per second. In 2012, the sailboy was used in the Canary Island region. Again, the measurements were conductivity, temperature, and oxygen. This project became a little challenging and needed to last a bit longer than originally planned. First, wind became a challenge. Out of bad luck, there was far less wind during the project compared to what is normal for the season. For a period of times, the sailboy stayed put in one position and slowly drifted off due to currents. Second, the instruments became subject to biofouling, which most likely could have been easily prevented using biofouling preventing coatings. For more information on these projects, a project in the Arctic Ocean near Svalbard, north of Norway, and much more, please see www.sailboy.no. For possible usage of the sailboy for the oil and gas industry, we have discussed these and other applications. Hydrocarbon leakage both naturally from the reservoir and after incidents. The sailboy can be equipped with wireless in-sea communication and act as a communication relay between subsea equipment and satellite communication. And finally, during offshore crane operation, the sailboy can be used as a scout, staying weatherwise upstream the crane vessel and report wind and wave data back to the vessel. Hence, the weather window at which the operation can be done can be expanded. Thank you very much for your attention. Again, please see www.sailboy.no.
Now I'd like to introduce our last speaker, who is Ian Reid, the CEO of Census, the Scottish Centre of Excellence for Sensor and Imaging Systems. We've asked Ian to give a short presentation on some of the excellent research being done here in Scotland for those of you who had expressed an interest in forming partnerships with researchers who could help you face the technical challenges of your business. So without further ado, we'll move on to that presentation.
Hello, my name is Ian Reid. I'm the newly appointed CEO for Census. Census is the Centre for Sensor and Imaging Systems. It's one of a tranche of 8 innovation centres in Scotland, and it's a key part of Scotland's innovation landscape. Our remit is to look at encouraging increased R&D intensity across industry and academia, particularly improving the coupling between the academic research base and industrial applications, and facilitating the efficient and effective uptake and exploitation of academic research by industry, generating economic value in Scotland. Obviously, we have a very broad application space in terms of sensors and their potential applications, but today we're going to focus on the subsea area. So first of all, why is Scotland such an important potential partner of interest for working in the subsea marketplace? Scotland has a long and successful history in a core segment within undersea engineering, and that is the offshore oil and gas marketplace. This is about exploration and extraction. It's a key sector in the UK, employing some 440,000 people. There are over 3,000 enterprises in the Scottish supply chain, up 166% from 2008. What's perhaps less well known is that this supply chain is very active in export markets and actually underpins nearly 50% of the global oil and gas offshore market for exploration and extraction. Services include technologies and products and value-added services ranging from engineering, scientific, robotic systems, sensor systems, services such as environmental surveying, environmental consultancy, and undersea surveying. Of course, the subsea marketplace is far wider than just oil and gas. It may include, for example, offshore undersea mineral extraction, seismic measurements, the management of fisheries resources, building and operating undersea infrastructure, including condition monitoring and through-life management of undersea facilities. Some 370 of those 3,000 companies in Scotland already have interests in the wider subsea marketplace. This is a key market estimated to be about $35 billion and set to double over the next 5 years. Scotland's on course to capture 36% of this worldwide market, offering such services as licensing consultancy, 3D mapping, new techniques for exploration and extraction, and a whole host of other technology-based products and services. Has pioneered the sensor stack, which is a good way of thinking about how fundamental technologies get to be used in wider end applications. The stack basically starts with the underpinning technology, which is at the sensor element level, through packaging of sensors, their calibration, and then communications to and from the sensor, including more sophisticated network architectures, through to taking the data and turning it into useful information by processing, analyzing, presenting, and visualizing the data. So what I've done is I've looked at that stack and I've just taken 3 examples of successful companies, of which there are many others in the Scottish supply chain, and I've just linked those to particular places in the stack. So let's take, for example, at the base of the stack, Tritech, which is a company based in Aberdeen with particular technical expertise in sensors, including sonar systems. And then let's take a look in the middle of the stack, FMC Technologies, another very successful organisation employing some 250 people in Scotland in R&D. And their key expertise is linking together sensors undersea with a fibre optic based undersea network architecture. Through to the top of the supply chain, a company that was a spin-out from St Andrews, that's Addis Deep Ocean, whose expertise is in digital terrain mapping and 3D visualization. So how best for a company to get a window onto this academic base and this industrial base and to start building relationships to access and leverage these key pieces of expertise? Scotland is very well established in the general sensors market, an industry worth £2.5 billion in Scotland and growing very strongly. That sensor market could underpin a broader subsea sector worth nearly £9 billion, according to the Subsea UK survey of 2014. Sensis, the Innovation Centre, has links to its sister innovation centre, the Innovation Centre for Oil and Gas, or OGIC, and working with either of those innovation centres gives you a seamless window onto the activities of the other. The Oil and Gas Centre is, of course, more closely linked to the end application for offshore extraction and exploration. Working with Sensis allows you to access the academic base, and Sensis can help you build R&D projects driven by specific issues of duration 6 to 18 months and actually fund some of the work in the universities. On the other end of the scale, strategic research projects of 2 to 3 years duration are also possible. Also in the toolkit for Sensis is the Enterprise Skills and Training Agenda, which allows for places on an MSc, an NGD, and a CDT postgraduate training course, which are sensor and imaging system specific from a technical point of view and very closely linked with industry needs and requirements. We can assist you in understanding the landscape for research and also the industrial base. We can help you shape projects which are fundable not only by Census but potentially by the Scottish RDAs or indeed the wider UK Technology and Strategy Board, or, given the right eligibility criteria, EU Horizon 2020. We can help you build those consortia and to develop an R&D portfolio which is closely linked with the academic base, helping you develop products and services for the future. So, if you want to come and have an informal, exploratory discussion, please contact Census. We'll be pleased to hear from you, and look forward to working with you in this exciting area. Thank you.
So now I'd like to invite all of our speakers together, and we have a few questions that have been asked by the audience. So I'm going to direct this first one to Richard, and it's Simon has asked about overcoming the short-range nature of subsea wireless data streaming. How to overcome that? Use relays, network buoys? Perhaps you could start off the discussion.
Yeah, thanks. I guess it depends what level of bandwidth you're looking for. I mean, if you're looking for high bandwidth, then electromagnetic is the way you've got to go. If you're looking for low bandwidth but long distance, then it's acoustic. But both cases, if you want to travel longer distances, it will come down to doing relays, boosters at various points. And obviously, in terms of infrastructure, that means putting infrastructure in, or buoys in, or subsea assemblies in with battery power to cover these. The alternative would be to take from subsea up to the surface buoy and then relay that by satellite elsewhere. So I think these are kind of the main ones. But typically you need some sort of relay, either surface relay or a series of subsea relays to carry the distance. Yeah.
Mm-hmm. Anybody else like to address that question? No, if I can then, because Simon has one follow-up question, which we'll move on to now, and he's also interested in subsea sensors operating in a 40 to 60 meter high velocity tidal waves to carry out environmental data collection. I'm not sure if this is something the panel feels that they can address.
I think it's a difficult one. I mean, because Simon's not told us kind of how many sensors or what kind of sensors. I mean, if they're on the seabed, then I would suspect wired and put down firmly on the seabed is probably better in high velocity streams. I mean, if you put in temporary or lightweight seabed wireless structures, then you've got a chance of them moving around. In terms of waves, if it's wave motion, then I think again anchored systems are required. So I think probably in this case it'd be more a wired system, or in the case of floating buoys, a wireless system. But certainly for the seabed stuff, wired. It'd be hard to see how you would retain integrity with a wireless system in high velocity streams.
Mm-hmm.
I think I can add to that. Actually, this is Blair here. We've done a number of, as was suggested, it would generally be in either a wired situation or possibly, battery mounted with some data recorder device. And we've certainly been involved in a number of environmental studies, say, for example, around the situation of undersea turbines, for example, or for doing scour monitoring, real-time monitoring. So if you're not as interested in seeing the data in real time, then we can record that locally, wake up the sensor, record the data and come back. And we've had very good success in operating it in very high turbid environments, almost more than zero visibility. So for example, watching a real-time active dredge situation, be able to cut through the sediment noise and see the tool operating. So we've had very good success of that because of the duplicity of the data that we have.
Okay. Any further comments? If not, it seems to be a lot of interest in wireless. So the next question we have kind of comes out of using sensors in the defense industry, and that's that one of our participants is speaking about wired versus wireless from a security perspective. So given that people often in a security context go with wired communication, they go with wired communication so that because it's more secure. You don't have to worry about somebody intercepting that data. Now, I know, Richard, in your presentation, you were specifically looking at the advantages, and you mentioned speed, which is one reason also above the speed you go wired, and also reliability. But you didn't mention the security of the signal. So if you're in the defense industry, for example, should there be any concerns? Is there any thought being given to the security of the wireless signal?
I think the answer to that is yes. I mean, most of the best encryption systems at the moment are based on military systems. Obviously, I mean, if you go and start looking at things like missile control systems, then obviously you require very secure communications with your missile, or it's got to be autonomous. So all of these things need to be very secure. So the defense industry has already very high-grade encryption for transmission of data. Whether it would use underwater is less clear. Submarines would typically come to surface and then broadcast by wireless satellite. I suspect the major sonar arrays are wired sonar arrays, again, to mitigate security leaks. So I think there will be requirement, well, there definitely is requirement within the military sector. Whether they're looking at it particularly in terms of subsea sensors or not, I don't know. But within the oil and gas sector and subsea industrial sector, then if you are going to scatter, say, a series of sensors and want feedback, some of it may be okay to leave fairly open because it may just be data coming back in again and you're not worried about security. But there may be things, particularly if they are to do with flow rates, which may be fiscal, and so on. There may be things where you actually want a secure flow of information back, in which case secure encoding is important. There are new encoding techniques coming up which also allow faster transmission or better transmission underwater based on chaos theory. So there are chaos theory based encryption techniques, but there's some work on chaos theory encryption for transmission, which can be quite secure.
Anybody else like to follow up on that? All right. The next question we have is from Terry, and it's a relatively general question, so I'll just push it out to the panel, and one of you can pick it up. But it's a question about global markets. So the question that this participant has is, which global markets and sectors do panelists see affording the greatest opportunities in the areas of subsea technology development and deployment?
Yeah, that's an interesting question. I mean, obviously the hot spots have been oil and gas up until very recently, but I think there's a huge amount of interest in subsea mineral extraction, for example. There are, as you know, certain parts of the world where subsea sensors for seismic activity as early warning is very important. But interestingly enough, I suspect in the near to medium term, it's actually back to the oil and gas industry again, but some end-of-life stuff to do with decommissioning of platforms and infrastructure.
I think I'd agree with that. I mean, I think particularly with the environmental side of decommissioning, there are huge opportunities, both in the long term and the short term, I think, in terms of sensors. The other area, certainly in terms of the oil and gas sector, is the move towards subsea processing, and therefore the requirement for subsea sensors which will last 5-10 years, subsea, give feedback on flow rates, pressures, temperatures, multi-phase flow, major problem, good multi-phase meters on the surface, but not so good in subsea. So there are quite a number of areas within subsea processing area as well, which are coming up.
Blair, I know that you're Code Octopus is involved in construction, for example. How interesting do you find that to be in terms of market opportunities?
Yeah, I think that's absolutely right. And what we do find is there's extreme parallels actually between what I would call the shallow water marine construction environment and also the deep sea. I mean, pressure and the lack of other backup systems is really the issue when you go to deep water, but it's really this similar kind of task, but obviously with a very kind of higher grade of potential risk. We are being challenged all the time, in actual fact, now to do the mundane tasks, if you wanted to say, or repetitive tasks. How can we do those quicker and cheaper? And what I sense the oil companies are looking at is how can we spend less, I guess, on the construction effort, but to do those things bigger. That will then reap rewards on all the other down the line processes, because the more construction there is, then the more we have in play in terms of production, the more subsea monitoring, and and it goes on from there. But I would also concur with the decommissioning side, but also kind of play into that, inspection, repair, and maintenance as well is also a big uptake area that we look at. What we do find is some of the deeper water and the areas, if I use the Browse Basin in Australia, for example, there's absolutely no visibility there whatsoever. So where we're definitely being drawn in is in the areas where they physically can't operate, the ROVs can't use their cameras, we can't use any other sensors, and we can provide a real-time three-dimensional control image for the people to operate, not only the ROVs to fly around, but for the construction team to do their tasks. So I would say all of those areas are very kind of high profile and carry with them some amount of risk. So people are trying to push the boundaries with technologies every day.
Yeah, I think I'd come in with that. I mean, I think you're talking about asset integrity. I would absolutely agree with that. I think the holy grail probably for pipeline inspection would be to have an AUV running down a pipeline and coming back with detailed information of the pipeline condition, not just whether it's shifted or scoured, but actually its wall thickness, its corrosion, and so on. There's some work on quantum sensing, which may give us more sensitive magnetometers to allow that, but that's still a long way away, I think, or a bit away at the moment.
Yeah.
Designer guys, would you have anything to add, or maybe some comments on things that your institute is doing in terms of new markets?
I think I agree very much with what's already said, but I do also think that oil and gas exploration going subsea is a trend that has just started, and reports from companies like Rystad Energy says that in short to medium term there will be some topside developments, but in 10 to 20 or maybe 30 years from now, most development will happen subsea. What's also interesting, I think, to add there is that at least from Norway we are going further north, closer to more vulnerable areas, and leak detection will be prominent. Will be very, very important to have, not only to have, but to prove that you have decent leak detection, so that you can stop any oil spill very, very quick.
Okay. Actually, Simon, who has been asked a question before, would like a follow-up, so we'll let him follow up the question. So this one would be directed to Richard, and I'll just push that out to you. So, could deployed sensors be used to help pinpoint for recovery faulty tidal turbine array power cables, again in a 60-meter deep installation in a high tidal flow environment? We're asking the tough questions for the last 5 minutes here.
So can you repeat that just for a second?
I will turn the screen so you can see. So could deployed sensors be used to pinpoint for recovery faulty tidal turbine array power cables in a 60-meter depth in high tidal flows?
I must admit, this is probably beyond my technical capabilities. I need to refer back to some of my colleagues on this one. I'm not sure. I'm not sure how you would.
So you've managed to stump the panel.
Yeah.
We congratulate you as the participants. But of course, if there are any questions that haven't been answered, we're always happy to come back to them.
I'd be quite keen to speak to some of my colleagues and come back on this.
Yeah. So we'll have a website, for example, that is going to have the full version of this webinar, including this Q&A and all of the videos in their proper form. And for any questions that you might have, you can email leadership@oxint.com and put up answers to those questions, or email you individually. Again, if you're looking to form partnerships, for example, with Scotland, you can get in contact with Ian Reid, and we'll help to set that up. We are getting close to time, but I think we have just one last question that we'll ask. So we'll push this out. So the question is that there are a number of surveys taken at a site by various contractors and research groups. The problem of real-time data in a tidal stream is extremely challenging, mostly due to cable wear. So what are the barriers to using wireless sensor systems?
The primary one, I think, would be just making sure your infrastructure stays in place. I mean, if you're a high tidal stream, you've got possibly more mobility. If you were going to use, you probably couldn't use acoustic. If there are high tidal streams or you've got acoustic noise, then you may have problems with acoustic transmission. If it's relatively short range, electromagnetic over the tens of meters would work. So EM over tens of meters, acoustic, I think if you have wave breaking, if you've got high speed flows going past turbulent or objects which will give high turbulence, I think there'll be problems. So I think that's probably the major problem in terms of the type of system we're talking about here.
Anyone else from the panel before we close up this session?
Yeah, I think the only other thing that we tend to run in as well, I mean, we're a real-time sensor, but there is, people do play on the term of real-time, so you can have this kind of delayed real-time, much like this video, we'll talk and then you'll maybe hear it a second later. So there is also, and we've done some stuff using above ground wireless, where as long as you can have a store and forward type mechanism, then as you say, if you've got sediment in the water, that maybe obstructs the flow of getting the data across in that particular moment. But maybe if you can delay and compress that data and then continue to send that, as long as you've got intelligence at the receiver and the sender, then there's some more that could be built into the infrastructure, I'm sure, around these where you've got more, challenge request information on how you send the data. So as long as it's not just a constant stream that's required, then you could do more and then sneak the bandwidth when you've got the opportunity to do so. And that's maybe another approach that if the data is not absolutely required, the second it happens.
Great. Well, we've about used up our hour. So I'd like to thank all of the speakers for being on the hot seat to answer the questions from the audience. I'd also like to thank everybody for listening. I would remind you that there'll be a website where you can listen to this event in full. We'll also have answers to the questions that you all kindly answered for us. Those will also be available on this website, and of course any other information that we think might be interesting for you. If you've enjoyed this session, please feel free to email us. Also, if there's other topics that you might be interested to hear about, we'd also like to hear about that, because I know as our sponsors, Scottish Development International is kind of interested in providing you a space to converse, get together, and debate some issues in terms of subsea sensors. So with that, I'd like to conclude. So again, thank you very much, and we hope to hear from you again soon. Thank you.